also try to get, okay, let me see if I can get this. Okay, so let's get started. And so one thing I was thinking about how this is working out, and I think maybe the thing to try to make clear is I think the best way to do this is that since there is this book or this textbook with very detailed kind of notes about what I'm trying to do, that what I'm trying to do here in the Zoom session is more is not go over every detail of what's in the notes. And I think, I mean, it's probably some of this stuff, it's better if you read through the details there. But what I'd like to do is mainly kind of concentrate on spending time, going over kind of what are the main points, emphasize, what is it that you really should be paying attention to, and also as we go along, kind of, realizing which things are actually likely to be confusing, and try to kind of go over, explain some of the more confusing points. So it'd be helpful if what you could do is before. I'll begin each class. So when I start in a minute. I'll begin each class asking for questions from the last one. So if there are things that I talked about last time that you still are confused about, we can start spending a little bit of time on that. And then what I'd like you to do is for each class try and read in advance the chapter that we'll be talking about. So it's typically each week, each class, it's going to be a new chapter. Today we'll be talking about what's chapter 2, which is about the group U1, and then the next Tuesday will be chapter 2. So now it's chapter 2. Next Tuesday will be chapter 3, which is about the group SU2. And if you then as we go along, as I'm talking in class, I'm hoping that whatever I'll clarify things or make things clear that you may have wondered about when you were trying to read this thing the first time. And you should kind of stop me if there's something which you didn't understand looking at it earlier and you're still not understanding when I've talked about it. Yeah. Anyway, turn on your mic and immediately, and speak up and say something and ask a question. And that's the basic idea. But I'm it's kind of a warning that there are some more points in the notes, often kind of points of exactly how something is defined or details of how to do something, or slightly off the main line kind of facts or things which are worth knowing. They might come up again later. I just didn't think I wanted to take time in here to try to talk about them. Okay, so any questions about any of this or about from last time?
I have one.
Yeah.
Jacob, hi.
Hi.
And I don't know if I should know this at this point. But with you have the notation, which I believe is for the wave function with the angled brace and then the vertical bar. Should I know what that mathematical object is, if it's a vector or a function or?
It's just a vector, yeah. So that's good. Let me just say some more about that. That's kind of a. So this is just so this is just the notation. So the thing you should know is that there's this thing I'm calling curly H, which is physically, the physics name is the state space, but from the mathematician's point of view, it's really just a complex vector space. Okay, and so what this just means is mathematically means you can take complex linear combinations of things and still be in the vector space. Now So physicists have a notation they use that goes back to Dirac. It's often called the Dirac notation. And so what do you want to kind of call elements as vector space? Also, maybe one thing to say about this vector space is that if it's finite dimensional, then this really is just n copies the complex numbers. It's really just kind of a column vector of n complex numbers. So at the beginning of the class, especially, we're going to be at the beginning of this class, we'll mainly be talking about finite dimensional. These are finite dimensional vector spaces, and then we're really just doing linear algebra, and it's just Cn. When we get at some point, it gets a lot more complicated that we start talking about infinite dimensional vector spaces, typically spaces of functions, which are which are kind of not just linear algebra. There's analysis or something going on. But the typical notation that a mathematician would use, they would say, well, this is just a vector space. It's just a big V, and I'll call things. So I'll use small b for vectors in here. What physicists would like to do is to say that is to write elements in here with this symbol, and then some kind of symbol in here, which is this is just a label. This is just a label for the vector, and this is the Dirac notation, and this is often called a ket. And I'll say a lot more about this as we go on, but it's kind of a joke. The idea is that if you take dual vectors to here, you can write them. You can write them like this, and this is an element of. Well, I'll say a lot more about this later. This is an element of the dual space, and this is called a bra. And then the idea is that when you can put if you evaluate this dual element on this element of the vector space by psi you get a bracket, and this is actually going to typically be the this is going to be the inner product of two states using the Hermitian inner product. So so we'll say more about this as we get to it. But what I'm doing right now, everything is just I'm not talking about dual vectors, and I'm not really using the Hermitian inner product in any interesting way. So right now, all I'm doing is this is just a notation for a vector in a vector space.
Okay, thank you.
Okay, yeah. But this is definitely one source of confusion. Any other questions to begin? Okay, if nothing else, then let me get let's get started. So this chapter, if you have looked at it, you'll find that it's kind of weird, and that when I started writing it, I kind of started out with trying to go over some of the high level theory. The idea is this first chapter is to try to give you kind of the simplest example of what's going on. But before, there's a problem with giving you a simple example of an abstract theory is you kind of need some of both. So when I wrote this, I think I wrote it a couple of different ways. I tried writing down the simple example first, and then the abstract theory, and then but that really made even less sense than writing down the abstract theory first, and then the example. So what I'm going to do today is go over some really kind of high level abstract theory about what representations are, and then shift to very, very concrete things, the kind of the simplest possible examples. Okay, but when I'm doing the abstract theory, you should find this somewhat confusing in the sense that I hope the statements will be kind of clear enough. But if you haven't actually seen any examples of an abstract theory, it's very hard to figure out what I'm talking about. But let's get started. So and to remind you what the big overview from last time. So last time I was trying to make it the argument that a way of understanding the subject is that you've got quantum observables are going to correspond to the to the operators from a unitary the algebra representation. But of course, the problem is that I haven't really defined any of this. This is just kind of abstract terminology right now. So what I want to do is go over this a little bit again, kind of say a bit more about what the abstract nonsense is, and then work out in detail one kind of in some sense the simplest possible example. And let's see. So okay, so maybe before I do this, maybe I'll give the motivation again when I get to the to give you the motivation when I get to that. But so let's go back to what what are we talking about? Well, we're talking about, I think, let me start with the most kind of abstract possible thing, and it's really that so I talked last time that you've got a group. I'm gonna write capital G. It'll be some group, and then the group acts on G acts on a set X, and so what this just means is that some X that you've got some operation that takes a point X to a point G dot X, element of X. Okay. So it's just a group action is just a thing where each group element kind of moves all the elements of this set around, and if you multiply two group elements, it's just a composition of the group action. So this is anyway, this is the kind of most general kind of thing. But then what you want to do is you want to have a so this is an action, group action. But now we want a representation. So this is just where the set X is a vector space. And V goes to G dot V. So vector space V. And so if V is a vector, then the group is acting on the vector space by something I'll write this way: pi of G times V, where this is a linear operator. Okay. So a representation is, one way of thinking about it is that it's a group action, but where you're not just acting on some random set which has no particular structure, but you're acting on a vector space. So you have to be told what V is, just as you had to be told what X was. And then this action symbol is really now just a linear operator times vector. So if you like, if you've chosen a basis, this is now like a column vector, and this is just a matrix. Okay, and so the condition that it actually be an action, that if you do one thing and then another, you get the same thing. If you act by one group element and then by another, you get the same thing as if you acted by the product of the group elements. This corresponds to okay. So one way of saying this is that G element of G goes to pi of G. So if we've got a group element, we've got these operators, and so I'll call this map pi. And this is pi. This is pi of G. And we say that the condition that this be an action is that this is what we call a homomorphism. I should say this differently, that in the sense that pi of G1, pi of G2 is pi of G1, G2. And so homomorphism is kind of a very, very general mathematical thing. It just means that you've got a map that preserves some structure, and here it preserves the group law. That the group law there's a group law right here of multiplication of linear operators. And there's a group law in here, and when you say it's a homomorphism, you mean this, which you mean it takes anyway. It takes multiplication here to multiplication here. Okay, so yeah.
What was what law is it preserving? Just the same. It's preserving the same operation.
Well, on one side here's the group law. Okay, this is so this group may come up in some very abstract way. It's got some group law here. Here these are linear operators, and it's it's just composition of linear operators. Actually, but maybe there is the reason in the notes I say this in a different way. Let me say it that way, and that maybe make you a little bit happier, which is this. Okay, so when I say that pi is taking an element of the group to a linear operator, well, if you want this to work, you can show that this linear operator has to be invertible. It has, because any group to be a group it means that an element of the group has to have an inverse. Well, same thing. Your pi of g has to be an invertible linear operator. So let me rewrite all this in this language. So let me just say it this way. So a representation pi, I'll write it sometimes this way, of g it's a homomorphism pi takes g to invertible linear operators. And then if V is finite dimensional, then one thing you could do is choose a basis. Choose a basis, and then pi of g is a n by n complex matrix, complex invertible matrix. Okay, and then so what we can do is we can then say that so you have pi is a map from G to the group to the invertible linear operators, which are, if you like, the invertible complex n by n matrices, and we can give that a name. So this is what's called GL of NC. Okay, and so this is a group. So this is called the group of invertible. It's just what I wrote there, of invertible n by n complex matrices. Okay, and so and GL just means general linear. So L means that these are linear maps.
Right. Okay.
They're general in the sense of the most general invertible one. Okay.
Sure.
Now so if you want to think about what this this I've kind of reformulated maybe this in a way a little bit more about what you're asking about, is that pi is a map from one group to another group.
Right.
And it's it's a group homomorphism.
Okay.
Okay.
Yeah, that makes sense. Thank you.
That's good. And now okay. And so I should say, actually, when I first started learning about representations, I think for a couple of years I was actually very confused when people talked about representations, because what you'll see when somebody talks about a representation, sometimes they'll say the representation such and such, or they'll say the representation V. And so sometimes they'll just tell you what V is, and that's kind of, and that's sometimes the right thing to say, because if you know what V is, it's kind of obvious what from the definition of V, it's obvious how the group is going to act on it, and so so pi is kind of determined. It's kind of obvious what pi has to be. So sometimes if you do it the other way, sometimes people will tell you what pi is without telling you what V is. And it just because once you know pi, it's obvious what it's acting on. So, but if you really want to know what a representation group is, you have to know the group, you have to know what space it's acting on, and you have to know what this map is. All of that data together is the representation. But sometimes people will only refer to part of that data when they're talking about the representation.
Okay. I'll have to look back at my modern algebra book.
What?
Then I'll have to look back at my modern algebra book.
Yeah, okay. Anyway. Yeah, well, I mean, I have a strange education, which partly by physicists and partly by mathematicians, so that's part of why I was confused. But anyway,
Okay.
so this is for general groups, and there's one example which I think I've forgotten whether it's in the problem set, and it's definitely in the book, which is kind of if you take just a finite group, where this is just a finite number of elements, and then you can. And then really what this is that this is really just a set of it's just a bunch of matrices, one for each element of G, and they satisfy this property of consistency among how you multiply things. But
Professor?
Yeah.
What would be a very elementary example of G and pi of G?
Okay. Sorry, you wait about 20 minutes. Okay. So the second half of this lecture will be answering that question. Yeah. And as I agree, it's bad pedagogy to do some abstract thing without giving you an example. But the problem is, but anyway, I ended up doing it, just starting with the example and then trying to do the theory also is confusing. But anyway, you got to start with one. I promise you'll hear more than you ever wanted to know about the simplest example in a minute, in 15, 20 minutes. Okay. So let's see. So that's okay. So if you're just dealing with a finite group, then it's just a collection of matrices. But now we're going to be interested. So to say where we're going with this is we're going to be interested in, we're interested in Lie groups, where G is a manifold, and so G is not just a finite number of, it's not a finite set of group elements. It's some kind of space with an infinite number of points in it, which fit together to form some nice smooth or some space you know how to differentiate on and do analysis on. That's what a manifold is. Okay, and we really care about and want to study the derivative. Okay, so so we'll say a lot more about this later, but just to kind of put this kind of abstract nonsense into the context of where we're trying to go, I want to say these are we're going to use these guys and we're going to work with them, but when we're trying to connect to what's going on in the operators in quantum mechanics, into these observable operators in quantum mechanics, what we're going to do, if you've taken a quite sophisticated course in manifold theory and then in a differential geometry, then you realize that if you have a map, if you have a map from this manifold, that this guy is a manifold, you get a map from this manifold to this manifold, and you can take its derivative, and that's going to be what we're interested in later. But I'm not going to, and that's going to be anyway. So we'll get to that later. But for now, that's in the background.
Professor, is the unit circle in your book an example of a manifold? Because like near every point, the local space is like a real line.
Which example?
The unit circle.
Yeah, well, that's the example we're going to talk about. Yeah, so we're getting there. I'm just saying, in the general theory, in general, Lie groups are manifolds. This is a manifold. So a homomorphic, a representation is a smooth map from a manifold to a manifold, so you can take its derivative. But this is just kind of for whoever of you has actually had a course where that makes sense. I don't want to. We're going to do this. We're going to do this very, very explicitly in some examples, and you'll see this very concretely. Okay. Okay. Yeah. Do you have a question?
If we fix the group G and a vector space V, can we have different representation maps phi?
Yes. Yes. Yeah. 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 Very, very definitely. And we'll see this even in the simplest examples. It's very yeah. And then yeah. Anyway, you'll see this actually. What I'll be doing in the in the first example, I'll take the simplest possible representation, and the same vector space C, there's going to be an infinite number of possible pi's. Okay, another question? Okay, so maybe there's just one thing. So one more piece of terminology is so here we're just telling you about what a representation is. So this is so pi v is unitary if if V has a Hermitian inner product. And again, if you haven't done much with kind of complex linear algebra in a while, just also, wait a minute, in a week or two, I'll try to review some of the stuff. There's also a chapter in this book, chapter 4, which is kind of a review of linear, everything we'll need from linear algebra. But the idea was to try to get going first. I'll first be doing examples where you only need to work with linear algebra in 1 or 2 dimensions, so you don't really need much abstract theory. And then before we get on to higher dimensions, then I'll kind of review the abstract theory. But one thing, if you've looked at complex vector spaces, there's an analog of the usual inner product called the Hermitian inner product, and then you just then you say the map is unitary if it preserves this Hermitian inner product, in the sense that if you take pi of g and apply it to a vector, and you also apply it to another vector, it doesn't change the inner product. Okay? So this is the abstract version of what unitary means. It means there's a notion of distance and of angle on your vector space, and when you do these operations, it doesn't change it. And then the unitary. So and then if your pi's are unitary, then they live in a subgroup of this group. So you have a group called U of n inside GL and C. These are called the unitary matrices. And there's a condition for a matrix to be unitary. I'll go over this when I talk about linear algebra again. But a matrix is unitary if its adjoint is its inverse, and you show that that's the condition that would cause this to happen. But before, maybe at this point, is there one kind of source of confusion is what these groups GLNC and UN look like. So let me just say a few words about that before we go on. Let's see. So the thing to say about GL and C, the way the slightly confusing thing about this is that these are in some sense very, very general n by n matrices. They just have this condition of being invertible on them. And so what these are what this looks like is it looks like the set as a set. It looks like the set of n of all n by n matrices, complex. So this has dimension, the complex dimension n squared. Okay. But you have to watch out. You have to so it just looks like just looks like C n squared. But then the problem is that not every matrix is invertible. So there are matrices which are not invertible, and those are the ones whose determinant is 0. So what you do, so you have to subtract the matrices with determinant equals 0. But the condition on the determinant, this is just one, as a function of all the elements of the matrix. This is just one condition. So it's one complex condition. So you end up with kind of a subspace in here, but of lower dimension, which is dimension. This is dimension n squared. This is dimension n squared minus 1 in terms of complex numbers. And so here you've got the identity. So the identity definitely doesn't have determinant 0. But far away from the identity, there are these things with determinant 0. So as a set, as a space, this guy is just it's just kind of he looks just like this nice vector space of dimension n squared, but with this kind of subspace with this complicated equation describing it has been removed. Okay. So that's what you should think of if somebody tells you about this group. If you so UN is I'll say a lot more about this later, but this is a let's see. So this satisfies some much more a lot of restrictive conditions. So this is going to be like there's going to be some subspace in here which is there's going to be some subspace in here which is UN. Okay. Anyway, so you should think of this guy as really. Anyway, but U of n is going to have a complicated geometry, but he's going to sit inside GLN squared. But if you know something more about geometry and about topology, U of n is going to be compact. U of n doesn't kind of go off to infinity or anything. It's kind of a restricted, compact subset of GLN. See, but we're going to see a lot of examples of this, and the main example. Maybe the main example we're going to start with that's relevant. I'll start with that. I'll say what the example is now. It's going to be so we're going to start with GL1C, and what this is just 1 by 1 invertible complex matrices. So that just means complex numbers that have an inverse. So that's sometimes written C star. So it's the non-zero complex numbers, and then inside here you're going to have the unitaries are going to be. This is going to be it's just going to be a circle, if you like, and so the picture is these are going to be the things these are going to be the things with length 1. So you've got in your C star is everything you so here's the identity at 1, see, and then so GL1C C star is everything in the complex plane with the origin removed, and then then U1 is going to be just this nice kind of bounded compact region, the unit circle. So this is U1. Okay. So we'll get back. So that's the story about groups, I guess. But we got to what I need to do is to tell you a little bit more general representation theory before we start on. So we're going to get down to the question of what are the let's work out the representations of U1 is what I want to do today. But I want to first tell you some kind of general theory about how to think about what the most. This is more the standard thing that mathematicians do. How do you classify all possible? Let's ask the question. Let's not just start by looking at a representation. Let's start by asking what are all the possible representations. Okay. Well, anyway, let me get started on the representations. Okay. So. I mean, I gave this very, very abstract notion of what a representation is, but it is very kind of non-concrete and hard to, how do you find these matrices? How do you study them? And so what we so what we need to do is to say we want to say that a general representation is going to be something that's built out of simpler things in a specific way. And so let's first start with this definition. A representation and I'll call it pi v of G is irreducible called irreducible if there does not exist a non-zero W sub, so proper sub, a W that's a proper subset of V such that pi restricted to W is a representation. Or I used to say pi restricted to W and W is a representation. So the way, another way to say this is that there's no way to find the only kind of simpler subset of your V that's also a representation is going to be is zero. So there's no non-zero interesting sub-representations or things. V is in some sense the smallest. Is as small as it can be without being zero and being a representation. And so that's so this is the crucial term of irreducible. And so mostly what we're going to do is we're going to be studying irreducible representations. And then maybe let me say that you can so what you can do if you have your irreducibles is you can write given or let's just say actually given two representations, it's called I1 V1 V2, you can form the so-called direct sum. And we'll call this, I guess the notation would be I1 plus the I2, and it's going to be on the sum of these vector spaces. And so the way you can do this is just if you think in terms of matrices, it's just going to be a block diagonal. So this is going to be V1, this is going to be V2, and then you've got various blocks acting, and here you put pi 1 of G, and here you put pi 2 of G, and here you put 0 and 0. So you basically just glom together, make a bigger vector space out of these two vector spaces, and use this guy to act on the first part of the vector space, this guy to act on the second part of the vector space, and you can check that this is a new representation, but it kind of obviously has sub-representations. It's not irreducible. It can be reduced into these two pieces. Okay, so now I think I better just kind of quickly say there's some more general theory in here, which it's worth reading. But what maybe just let me just say let me just say what the general theorem is. The general theorem is really just going to be that if you're looking at unitary representations, then the most general one is going to be a sum of irreducibles. So here this is a sum of representations. But if you're given a unit, if you're asking what's the most general unitary representation of a group G, the answer is, well, it's the direct sum of a bunch of irreducibles. And so the problem is always going to be, this is going to be the big problem of the subject. If somehow you get hold of a representation, the way to analyze it is going to be to break it up into irreducibles. So the subject of representation theory kind of has two parts. How do I study the irreducibles, and how do I identify them and know how to work with them? And then and how do I, given a general representation, how do I break it up into irreducibles? So those are just kind of the two big problems of the subject. Okay. So anyway, then let me then there's one other kind of piece of abstract theory I think I better again say fairly quickly. So if you want to recognize whether if you're trying to recognize somebody gives you a representation, is this representation irreducible? Well, the problem is that you can't really easily tell, because if they if somebody handed it to you and they showed you the matrices and they were all in this block diagonal form, then you would say, sure, we're done. It's reducible into these two pieces. But the problem is that you may be handed these matrices in some other basis. Somebody may have done a basis change on you here, and so the matrices aren't block diagonal. And the question then becomes, can I find a transformation that will block diagonalize them? And that's actually a hard question. Okay, but there's one piece of theory that you can say, which we'll use, which is a general, and this is Shureslemma. And again, on the grounds that it would, I don't want to spend the time to do this carefully enough to say it understandably. I won't go over the proof here, but it basically says that if pi b is irreducible, and let's see, then the only linear maps M from V to V that commute. Let me say it this way, such that. So here I mean the commutator. So you've got these linear maps and you've got this linear map, and saying that the commutator is 0 means that if you multiply this times this, you get the same as multiplying this times this. So the linear maps are M equal lambda times the identity. So obviously, if M is just the identity matrix times lambda C, irreducible, and then and V complex. Okay. So it's clear that if you have the identity matrix, so it always commutes with all of these. But in general, what's going to happen is if somebody gives you a representation that's not irreducible, one way of figuring out that it's not irreducible is you can find some matrices M that commute with all of the representation matrices, but that are not just the identity. And then you can use by looking at the eigenspaces of those matrices, you can break up the representation to smaller irreducibles. That's the idea. But one thing that's crucial is that this only kind of works nicely if you look at the argument, look at the proof. It only works if these are complex vector spaces, and this in some sense is one reason we don't like to talk about representation theory over the real numbers, is because it's much more complicated, because this is no longer true. A lot more complicated things can happen. So that's it. And then if you
So I have a question. If V is a real vector space, but V has odd dimensions, but then is it true?
It doesn't. I don't think it has anything to do with the dimension with the dimension of the vector space.
So maybe I think for odd dimensional real space, it has a real eigenvalue for M. It always has a real eigenvalue, but because the odd dimensional polynomial always.
It's not that. The point is just that these are. I mean, the eigenvalues may be. I'm sorry. I think the product. I should ask you about that later. I should think about that later, because I'm not sure. I really. In some sense, the only reason I'm bringing this up is because I don't want to talk about real vector spaces. I'm sorry. I mean, there all sorts of interesting things happen, and it's hard for me to remember what they are and to answer you properly. So, but the whole point is, we're trying to avoid thinking about that. Okay, sorry. Okay, and so but one thing that you can prove with this, and the proof is again in the notes, is that the if G is commutative, so in other words, G1, G2 is always equal to G2 to G1 for any two elements of G, then then all irreducible representations are one-dimensional, are on V is equal to C. In other words, so the case of commutative groups, representation theory gets a lot simpler. It gets a lot simpler because you don't actually really need, once you break things into irreducibles, you don't really need matrices anymore. You're just always going to be acting on one-dimensional complex numbers. So all your representations will get C. And so that's what we're going to do in a minute. In a minute, we'll work out the simplest example, and that's where the group is commutative, and where you're going to have all your representations are on C. Okay. Actually, I realized. So sorry. I hope you. Okay. Okay. I'm sorry that I lost the chat window here. Let me see if there's anything I should. Yeah. Okay. Okay, I'm not sure there's anything. Yeah, I'm not sure there's anything I can answer right now. But anyway, so that's just so anyway. This is the goal that also, if you look at the notes, that there are subtleties about what happens if you're not using if your representations are of the real numbers, or if you're looking at non-unitary representations, and I'm trying to at least avoid those. We'll avoid those for now. But for now, I mainly wanted to get to this theorem, and you can see this theorem just by there's a quick argument that once you believe if you believe Shureslemma, then the fact that these guys all basically the fact that these all commute. Also, it means all the pi of g's have to commute, and the only way that they can all commute is by being a sum of irreducibles on one-dimensional things. Okay, so let's get on. Okay, so that's the end. That's the end of the abstract theory. So now I'm going to come back to Earth and try to actually see an example of all this stuff. So if you found some of this confusing and hard to figure out what is going on, that's normal. But now I should be saying things which are actually one interesting one. So the blackboard is still readable, right? Because one interesting thing about this class is that I've got light. This is natural light coming through the window, and as it gets darker and darker, I'm worried that. Please let me know. Speak up if all of a sudden that you're having trouble reading the blackboard. I can turn the light on.
Still legible, fine.
Okay, good. Okay, so now here we are. So here G is equal to U1. And so I mean, very explicitly, this is the group of, it's a set of all e to the I thetas with and then the group will of course just e to the I theta 1, e to the I theta 2 is e to the I theta 1 plus theta 2. And you can think of this as, so very concretely, it's the unit circle. Here's the identity. Here's the element theta. And then if you just, the way you multiply one element by another element is just by adding the angles. Okay. So you could also think of this as kind of an additive group as you're adding together the thetas, but then you have to remember to mod by 2 pi. So it's maybe better to not think about that, but to just think about all things like this, or geometrically, just think about all points on the unit circle. So this group, as a nice, it's kind of a nice simplest example of a Lie group. It's actually a anyway, it's a circle, so it has an interesting geometry, but a very simple one to understand and analyze. Okay, so that's the theta. Now what are the okay? So now let me give you a theorem or the main claim, the main theorem here is that all irreducible representations of G is equal to U1 are given by, let's just choose so let's call it the pi, and we'll put a k here, and then pi k is the thing which if you take e to the I theta, you get you just get e to the I k times theta. And this is going to be, and you can do this. This is going to work consistently whenever for k is any integer. Okay, so this is so to the question about what are the and these are all acting on, and you're always so here's an example where I'm not actually telling you what v is. I'm just telling you what pi is, because these are all just acting on v is equal to c. Okay. So there's lots and lots of I mean, we've got one v and an infinite number of irreducible representations on that c. And so when I talk about these guys, I'm always talking about the pi's, and I'm not talking about this guy because he's not the relevant information. Okay, so then if you want to prove this, let me start with it. Proof is a little bit so trying to think whether it's worth trying to decide whether it's worth to go through this proof carefully or not. But okay, let me, since you've got the details of the proof here, let me just kind of go through it a little bit carefully and tell you kind of what the crucial steps are. So you basically, what are you trying to do? You're trying to, if somebody tells you you have an irreducible representation of U1, you're looking for a map pi from, well, maybe to say it explicitly, to say you're looking for a function. So pi of theta is some function of theta. So some function of theta, and such that okay, so you need f of
So are you implicitly saying the only space of the only space V should be the one-dimensional space?
right? Yeah.
Oh
no, but okay, but that because sorry, yeah. So this theorem that I showed you earlier from Shureslemma, that says that if the group is commutative, all the representations are one-dimensional. Okay. So that general theorem says that if we're going to do that we only have to look at these. Okay, that was the point. That was the reason to do the general theorem. Okay, so now I realize I confused it. So the okay, I guess I've written this in a confusing way, but the okay, so we're looking for a function. Maybe I should probably write this in a slightly different way in the notes. Let's see if I can get this to work out. But you need, so we're looking for a function pi of theta, right? And where theta is the angle. Okay, so now there's one thing which I need to okay, looking for a function pi of theta. But now let's consider. Okay, so let's consider. Let's consider the derivative. So this is taking us from R, but where you're identifying things mod Z to the non-zero complex numbers. Okay, so this is it's GL1. Actually, if it's going to be, yeah. Anyway, anyway, so it's going to be so pi of theta is going to be a non-zero complex number for all theta, and if you change by any number of 2 pi's times an integer, you'll get the same thing. It's a periodic function. So we're just looking for periodic complex valued functions like this. So the trick to the whole thing is to realize that we're now the circle is a simple example of a manifold. It's something which you can actually take derivatives. Okay, so so now that if we have a function from the circle to the non-zero complex numbers, we can take the derivative of that function. And I guess one thing that I'm not gonna, so you might actually need to do this more carefully. You might actually need to build into this theory an assumption that your maps pi that I'm talking about are always going to be differentiable. And it turns out there's a very, very, if you try and look at non-differentiable functions or functions that are in some much more general class of, things that are just continuous but non-differentiable or non-differential functions, then you get into a much, much more complicated story. And there's the bottom line ends up being that, the fact that being, if you assume continuity, the group law actually forces differentiability. And so you only really kind of need to assume continuity. So I think here you should kind of assume that this is a continuous map. If you try looking at discontinuous things from here to here, then you can get into a different realm and a different story. But we're going to actually, to make things simpler, let's assume that this is differentiable. And so let's take the derivative, and the derivative is going to be a limit as delta goes to 0 of pi of theta plus delta. I guess I'll maybe call it delta theta. Sorry. Minus pi of theta over delta theta. Right? That's just this derivative. And then what you do is you then use the homomorphism, use the fact that this map has to be a homomorphism is a very strong condition on it. And so this implies that that this guy is now equal to you can now take out a factor of pi of theta. So pi prime of theta is pi of theta. And then what's left is the limit as delta theta goes to 0 of f. Okay, pi. Okay, so now pi of theta plus delta theta by the homomorphism property is pi of theta times pi of delta theta. So here you get a pi of delta theta, and here you get 1 over delta theta. Okay. But this guy, but this is pi of theta times this is the derivative. This is the derivative at theta is equal to 0. So this is just the number pi prime of 0. Sorry, pi prime at 0. Okay, and so. And so what this is, so this is just some constant c. So what you have is you have a differential equation which says that you're looking for functions whose derivative is some constant times the function itself. Okay, but you know how to solve that differential equation. So the solutions are that pi of theta is the e to the c theta, right? And it's the world's easiest differential equation. And then you require periodicity. so pi of theta plus 2 pi is pi of theta. Okay, and that this implies that k has to be, the only thing that will work is that the constant has to be I times k, with k as an integer. So anyway, so that's basically the argument, and the crucial trick is when I went from here to here, the fact that I used the homomorphism property. So the homomorphism property turned, just said that this guy has to satisfy a very specific differential equation, and it's an easy one to solve. And so the solutions are e to the ik theta for k integer. Okay, are there any questions about that?
This differential equation, or sorry, this requiring that this needs to be a homomorphism is what gives us this differential equation.
Yeah, it's just as I went from here to here, I used pi of theta plus delta theta is equal to pi of theta times pi of delta theta. This is what I meant by the homomorphism property. Okay, so I had to know this.
Right.
Okay, and this condition is strong enough to turn the derivative and to tell you that the derivative is proportional to the thing itself.
Right.
Okay. Okay, so let's. Okay, so now we know what all the irreducible representations are, and then so in some sense the bottom line is that any. So let me just say it again. So let me actually change to a physics language then, and then the what do I want to say this? Okay, well, so any. Okay, let me kind of then start re-saying kind of the general mathematical theory in kind of a physics language right now. So let me just say that any let's say this way. So if H is a U1 representation, or again, I'm being, watch out at what I've just done. I've just told you that the vector space, so is there exists a pi h for some pi, then. And it is of the form. Actually, maybe before I do this, let me actually just say what. Maybe just give. I'll just say this in words. Give some motivation for what the what the. Okay, so you expect to have U1 representations on your state space whenever you have a U1 symmetry, whenever you have kind of rotations by a circle symmetry in the theory. And it turns out that there's all sorts of basic examples in quantum mechanics where you have this U1 symmetry. And one example is the, actually, even if you're in 3 dimensions, if you pick a direction and look at rotations about that axis, that's going to be it's going to have a U1 symmetry. And so what this tells you is that, if your theory is invariant under rotations in a direction, then all of the state space is going to break up, and it's going to break up into pieces, one-dimensional pieces characterized by integers. And remember that I said that rotational symmetry corresponds to the angular momentum. And so what this is going to do is going to say that angular momentum is quantized. That angular momentum quantum angular momentum comes in integer pieces. And there's a similar. So maybe I'll just stop with that example. But that's one of the basic examples about why, in some sense, the fact that these U1 representations are labeled by integers corresponds to the fact that to the reason we call it quantum theory. It corresponds to, it actually explains why all these things that classically could be continuous are observables have become observables that if you actually look at them and see what values you can get, they're going to be integers. And so the whole kind of quantum of quantum theory is kind of built into into that theorem I just told you about. Okay, but then for general U1 representation, that it breaks up, it's given by, let's call it H. And now let me give it a different, let me give it a set some integers Q1 plus Q2 Qn. So where U1 acts on HQK, well, yeah, HQK by and these are all just one dimension. These are all one dimensional. So this big complex vector space breaks up into one dimensional things, and by psi goes to pi of e to the I theta. Psi is e to the I qk. Psi. Yeah, sorry, e to the I qk theta. And QKs are integers. Okay, and these things are these are sometimes called QK are sometimes called charges. Okay, so when somebody doing quantum theory talks about a charge, what they mean is that they've got some kind of, anyway, there's a U1 acting on the theory. There's a U1 acting on the state space, and it's acting in this way. And there's some kind of list of integers which tells you how the U1 acts on this. And these are going to actually be the so the IQ. So to get back to our kind of general thing is that if you act. So the charge operator Q is the operator so let's imagine so we've broken our state space up into into one dimensional pieces, and then on this one it acts by Q1 here, by Q2 on the second one, and then it's diagonal down to Qn, and the everything else is 0. So the I said we're interested in these Hermitian operators that are quantum observables. Well, the Hermitian operator that we end up with in this case is this Q. And he's really so anyway, he's just exactly this guy, and he acts. So he acts on the state space. So U1 acts on the state space on H by e to the I. By exponentiating Q, so e to the I theta goes to, let me say it this way, so the representation is e to the I theta Q, sorry, e to the I theta Q, so he's this guy, and so he's e to the I theta 1 down to e to the I theta n, and then 0 and 0. Okay, so this is kind of going to be the model of actually what we're going to try to do, what we're going to do in general. What we're going to do in general, we're interested in understanding the implications of having some Lie group G acting on our state space, and so we want to understand what the possible irreducibles are, And then for any given quantum mechanical state space, we want to then break it up.
Wait a minute. Is it theta 1 to theta n, or is it theta times q1 to theta times qn?
Oh, sorry. Yeah, sorry. Thanks. Sorry, this made no sense. Thank you. Sorry. Thank you. Yeah. Trying to get too fast here. Okay. Sorry about that. Okay. Yeah. So it's because everything is one dimensional here. Everything just becomes these, just diagonal matrices. Okay. So you want x this way. And so, and then now the way you get from, if you know the observable, so what the way the physicists say this is that the physicists say that this observable operator here, so we say that Q generates the U1 action. Okay. And so when you hear that somebody say that, I've got some quantum observable and it generates the action of a symmetry group on my state space, what they mean is this. And so you can see that what this Q you can get by just exponentiating. And if you're given the U1, if you're given the action of a Lie group on your symmetry space, you can differentiate it. If you can differentiate it, you can recover Q. So you can go backwards and forwards by taking Q. Yeah. So by exponentiating in one direction and going from one of these observables to an action of the Lie group, or you can, if you have the action of Lie group, you can differentiate it and recover the observables. Okay. So that's I think I've kind of run out of time to say more. One thing that maybe I'll say maybe a little bit about this at the beginning. So I was going to actually try to screen share you and show you a really, really confusing picture on page 21, but maybe it's better to just let you just kind of look at this in private and see if you can make sense of that. And maybe I'll start by saying a bit about that next time. But that's kind of the geometrical picture of the representation. But this is really pretty much all there is to say about U1 actions. I mean, they really, they're in some sense very, very important. That they characterize quantum states by these sets of integers, which are the charges of the state, and depending upon whether your U1 comes from rotations about an axis, or whether it comes from multiplying states by a phase e to the I theta, or we'll see when we do the harmonic oscillator that there's the Q's and the momenta and positions kind of fit together into a plane, and you can rotate in the plane, and then you understand why harmonic oscillators have integer energies. So there's all sorts. This structure will come up again and again, and it's kind of very simple. But let me stop here. Maybe I'll say a little bit about the general. I'll say a couple more things about this to start next time. The things I didn't quite get to, and then next time what we're going to do is just go to G is equal to SU2, and this is going to start to get much more interesting and much more complicated, because this is a group. This is the 2x2 unitary matrices with determinant 1, and these things are non-commutative. So so far the thing that you don't see here when you do this all theory is that the only operator that we're seeing is a commutative operator. So and the really trickiness of quantum mechanics only really starts once you have different operators that don't commute. So that's where we'll start next time. Okay. So any questions to end up with it? Yeah.
I have a question.
Yeah.
So you presented a theorem after Shureslemma, and
yeah.
I was wondering if that said, so it was, if G is commutative,
yeah,
and all irreducible representations are on the complex numbers.
Yeah, when they're one dimensional.
Did that say all representations on the complex numbers are irreducible?
Yeah, well, okay. So a representation on the complex, if somebody gives you a representation of a group on the complex numbers on C, it has to be irreducible because there's nothing smaller than C. You know, as a complex representation, C has no subspaces, right? C is, yeah, so there are no complex subspaces of C other than 0. So it's true by the definition of being irreducible that if you have a representation on C, it's irreducible. You can't break it up into two pieces. There's no smaller C's to put in there. So it's true that if it's a one-dimensional representation, it has to be irreducible. So the the point of the theorem is more that there are no, if your G is commutative, you cannot, and somebody gives you a two-dimensional representation, you know that it has to actually be reducible. If somebody gives you a two-dimensional representation, you have to be able to break it up as, anyway, yeah, you have to be able to break it up into two irreducible one-dimensional pieces. It's not irreducible. So the point is that for commutative Lie groups like U1, the representation theory is much easier because there are no higher dimensional irreducible representations. They're all one-dimensional. Does that help?
Yeah. Okay. Thanks.
Okay.
Yes, I also have a question.
Sure. Hi.
It's about the theorem 2.1 in your book.
Okay. So what's the question about?
I wonder if it's equivalent to the spectral theorem, because if you can reduce a unitary matrix into a block diagonal form, you can further do some basis transformation to make it diagonal.
Yeah, that's true.
Oh.
Yeah. That is true. So one thing to say about it, I'm just doing some kind of general things. So the this was one thing I kind of skipped a little bit because so there is but the basic idea is that if somebody gives you a unitary representation and they give you some complex subspace which is also a subrepresentation, then you can always take if it's unitary, you can take the complement with respect to that Hermitian inner product and get a representation on that. So whenever you've got unitary representations, you can always split them. You can always split them into irreducible pieces. And the thing that I was trying to avoid telling you is that if your representation isn't unitary, then that's not true, and interesting things happen. But the spectral theorem is really just a general way of saying that. I mean, when we get to linear algebra, I'll say that again, and the spectral theorem in finite dimensions, I'll say more about that. But it's essentially that same fact. That's right. This becomes a much more non-trivial subject if you start talking about infinite dimensional vector spaces. If you're then you're doing analysis, and it becomes much.
I mean, when we talk about infinite dimensional vector spaces, it's because it doesn't necessarily have a complete eigenspace. Yeah. So these two theorems are not equivalent.
Right. Yeah. So let me. I mean, one thing, a general thing to say is for right now, for the first few weeks here, you better assume everything is nice fine dimensional. We're just doing linear algebra, and then as we start to get to infinite dimensional examples, I'll try to say a little bit about the general theory. But maybe just a general comment that if you go out and get a book called Quantum Mechanics for Mathematicians, there are a lot of very good ones. There are the ones mentioned in my notes. A lot of them, what they're really what they end up doing is a lot of the trying to really get right a lot of the rigorous theory about how you deal with infinite dimensional state spaces and how all these how exactly the right statements are. When is an operator self-adjoint? What does that mean? And so I've kind of consciously decided in this course I'm going to try to avoid that stuff. I don't want to, because that's not that goes into interesting mathematics in a very different direction to the one I'm interested in. So for now, there's no analysis going on now. Everything's finite dimensional. When we get to the analysis, I'll try to, as we go on, kind of build it up and explain some of the analytic condition analytic problems that come up, but I won't kind of really delve into them and really prove theorems about them because that's really another subject. Okay.
Okay, thank you, Professor.
Any other questions?
I had a small question.
Yeah.
So in the very beginning, when you mentioned that representation pi v of g, in that case of finite dimension, we can choose a basis of n by n invertible matrices. And so if those invertible matrices were to be, for example, the 3 poly matrices and the identity matrix, so
if they were which matrices?
the 3 poly matrices and one identity matrix, then what exactly is V in this case? What vector space would this
C2. So this is exactly what I'm going to talk about on Tuesday. Okay. Yeah, and there the representation, there the irreducible representation is 2-dimensional on C2, and the Pauli matrix, and then you have the analogs of these Qs, then these become 2x2 block matrices, and they're given by the and the analog, and since you need self-adjointness, they're the Pauli matrices. Yeah. So, but that's really going to be. I'll spend all Tuesday talking about that.
Okay. Just another quick question. So. Just when you mentioned that, like immediately after that, in a representation pi v can, so if we have 2 representation pi 1 v1 and pi 2 v2, we can form a direct sum, and you show there's like block matrices. So is this like equivalent to within a physical system you have one particle and another particle, and you were trying to develop a direct sum of their eigenfunctions?
No, yeah. So watch out. So we'll talk about this in some detail later. But there's 2 things you can do. If somebody hands you 2 vector spaces, there's 2 ways you can combine them. There's the direct sum, but then there's also the tensor product. Okay, and so the direct sum is kind of a fairly trivial construction. I'm just kind of glomming these things on together, and everything is independently happy on each of them. The tensor product is a much more non-trivial business. And so, and if somebody gives me this physical system described by this H1 and this physical system described by this by H2, then if I want to describe the 2 of them interacting, I have to take this tensor product, and that's much more non-trivial. And so that we'll talk about later.
Which one is the one you use for today? The direct sum.
The direct sum, yeah. So it's the so it's the difference between V1 direct sum V2, and the thing that I'm not telling you about yet, which we will talk about, is the tensor product. And so here, if this has dimension n1 and n2, then this has the dimension of this is n1 plus n2, and really just what you're doing is just what I showed here. You're just taking, you're just putting, you're just putting vectors in here and the vectors in here and putting them together. Here, what you're doing here, you're doing something much more non-trivial. Here it's going to be n1 times n2. It's multiplicative. So here the dimensions are going to get a lot bigger, and you have to anyway. Here everything just kind of breaks up nicely. Here something much more complicated happens.
And just to clarify, when we direct sum 2 physical systems, it means that these 2 systems are independent and they do not interact with each other.
No, I mean, you should not think of this as corresponding to 2 independent systems. This is what, if you try and think about 2 independent systems, it's this guy. I guess maybe you're right. I mean, if you're not at all, if you're totally uninterested and don't want to say anything about these 2 things interacting, then you can just put them together in this way. It's true, but this is really kind of a trivial. This is kind of a trivial way of putting things together. I mean, these things just do not interact with each other. Here, you know everything about what's happening in here by looking at this separately and this separately. Here, you can get all sorts of interesting interactions. But you really, it's not a good idea really to think of this as being physically what happens if you put 2 different systems to get physically together. Because if you put 2 different physical systems together, this is going to govern what's happening, not this, because this can never tell you about interactions between the two. Okay, any other questions? Okay, well, if not, let me stop now, and I'll turn this off. And if people want to stay longer and talk and ask some questions, then just connect to the other Zoom thing. Okay, okay. Bye for now, and I guess I'll see most of you again on Tuesday. And yeah, and do try and read chapter 3 and see what you can make of it before next Tuesday. Okay. Bye.
Thank you, Professor.
Bye.
Thank you.